Thank you, Amber. Appreciate that introduction and context. And thanks, everyone, for tuning in. We have a very interesting topic today that I'm kind of excited to talk about. Open systems, residence time distributions, mean age analysis, flow characterization. This is an application space where M-Star really shines. And this idea of doing transient time accurate simulations really coming to bear. I'm going to be talking about, again, open systems today and talking a bit about residence time distribution interrogation and calculation, as well as mean age interrogation and calculation. Mean age is kind of one of those things that people know about, but they might not really know how to use. So I'm going to do a working demo of mean age in action and kind of talk through what this workflow looks like and what it actually gives us. Again, so today is open systems. I mean by systems that are, well, changing volume or maybe have some sort of steady inlet and outlet. Here, for example, is like a surge tank. We're looking top above this vessel here. We're looking down in the direction of gravity, watching fluid come in from the left, swirl around and exit and void down here at the tank. Let me pause this guy. Here I'm colorizing some of these tracer particles by velocity to see where fluid tends to get stuck. This is kind of cool because I can see like the first molecules that come in are colored blue. As time goes on, they shade over to warmer colors. And I can see I'm getting old fluid stuck in some regions of this vessel, which is undesirable for this process. But it's neat to see like, okay, well, once it reaches steady state, it gets some sort of steady state through the vessel, but it doesn't mean I don't have continuous recirculation of what might have come in initially and is stuck elsewhere. So this idea of kind of an open system with a transient fill level, of course, introducing some sort of non-constant residence time distribution throughout the vessel. We can have other source systems as well. Here's a semi-batch process. I'll have some sort of agitator, or I should say two impellers spinning. I'll have a free surface vortex begin to form, an unbaffled system. I'll add fluid. I'll speak to the system later on as well. I'll add fluid. At some period, I'll start to drain this fluid down as it reaches some critical processing condition. So now the level's going down. It's sinking as I'm pumping out this bottom drain down here. A good example of an open system, right? We have some changing fluid volume. Not an open system is changing fluid volume, but this one happens too. There, I turned off the impeller. I'm just letting it drain from here on out. But again, it's this system where I have inlets, outlets, fluid adding, fluid leaving, and some potentially complex fluid mechanics between the two. Simple pump here, progressive cavity pump, watching fluid come in, watching it get pushed around and exit, as it were. Again, and a side note, M-Star isn't just used for impellers and whatnot. It's used for all sorts of things, pumps, surge tanks, pipelines, whatever. But foundationally, again, a good example of me adding pressure to a fluid in an effort to, well, in response to the action of the impellers inside this pump. There's no volume change here. There's pressure change, of course, no volume change. These guys had volume changes. There's no volume change in this guy's either. I showed this one a couple weeks ago in one of our seminars. But again, an idea of an open system. Fluid in, fluid out. It's not just batch. It's not just closed. It's not just an impeller when I exited a fluid. It's actually a fluid coming in, fluid going out, and some sort of attendant residence time or residence time distribution associated with it. So all sorts of kind of fun open systems and residence times and whatnot. I have my two slides I always share. One, in M-Star land, we're always trying to model things at the level of first principles, right? When we're solving the transient Navier-Stokes equations, we're trying to do DNS and maybe LES, often LES if the Reynolds number is too high, but we're not immediately going for RANs or time average simulations or correlations. We're trying to solve the governing conservation law, the conservation of momentum here, as prescribed in Navier-Stokes. For particle transport, we're going to be modeling, wherever possible, every single particle. Now, that's not hard to do for these tracer analyses because, quite frankly, we only need enough particles to reconstruct an RTD. I mean, we may need to use parceling theory at times, the foundation of modeling particle transport at the level of the individual particles, whether they are inertial particles, whether they are tracer particles, whether they're DEM particles. We're modeling these carriers at their true form and advecting each, I should say, integrating the position of velocity of each particle individually and explicitly using Newton's second law in tandem with the fluid flow and coupling thereof. For species transport, we're solving the advection diffusion reaction equation. We're solving it in tandem with Navier-Stokes, right? So we're not using some mean flow field and stitching some advection solver on it, as it were. We're solving all these physics in tandem and in real time. So here we have gas bubbles being added to the bottom of the bioreactor. We're watching the gas bubbles move as individually tracked Lagrangian point objects move through this vessel in response to the agitation. We're seeing oxygen transfer to this aqueous phase and advect and diffuse through the vessel and react to the biomass consumption. But importantly, all these physics are happening in tandem in real time and are being modeled at the level of the transport carrier. Okay. Induction not shown here, same idea. We're looking at full 3D wherever possible. Second slide I always share, because again, I harp on this. This is made possible by advances in GPU technology. Okay, GPUs, we have a lot of newcomers here I can see today. GPUs are a little different than CPU architectures. GPUs are originally developed for graphics processing, are very compute dense. That is, a GPU has thousands, tens of thousands of compute cores on it, compared to a CPU, which has maybe 4 or 8 cores. GPUs have all the memory they need to access on the GPU itself. That's in contrast to a CPU, which has to go through your motherboard to talk to the RAM sticks, as it were. As this density of compute elements combined with this locality of the memory means that one good GPU, which is the size of like a maybe 5 Twinkies, as it were, if you're using my preferred unit of measure, will have the same compute capacity in terms of gigaflops and memory bandwidth of, well, actually gigaflops in terms of several hundred CPUs. So again, one good GPU has the compute capacity of several hundred CPUs. Okay, and if you're using that compute capacity well, the performance of your code on that GPU can match the performance that would be achieved using, again, a several hundred CPU network or cluster, I should say. The memory bandwidth as well also improves speed. And these are, again, kind of apples to apples comparisons against current GPUs versus current CPUs, as it were. And so this introduces a step change in how we compute. And I make this comment every time as well. Like, why is ChatGPT a thing now? It's because the GPU hardware makes it possible, right? All these changes we're seeing, whether it be in AI or other sorts of engineer-related processes, are made possible by these advances in the hardware. And so to think that us as physics-based modelers are immune from this is not true. These advanced architectures are changing how we're going to run these simulations. And importantly, not every code can run on a GPU, right? You can't take code written for CPUs in the 90s and just put it on GPUs and expect to see performance improvement. You've really got to write this code, line one, and think about the physics from construct one in a way that's going to exploit this massively parallelized environment with this very high memory bandwidth architecture, as it were. One kind of side comment here, because it comes up quite a bit, or not infrequently, I should say, is that, oh, well, are you really solving the Navier-Stokes equations when you're using these cellular automata or Boltzmann transport equations to solve for momentum transport? And the answer is, well, yeah, in the same way that we're all solving the Navier-Stokes equations. So just to be clear, within the context of M-Star and any GPU native solver, like, we are solving the Boltzmann transport equation in a way that recovers the Navier-Stokes equations. Okay. So said again, no, our governing equation transfers Boltzmann transport equation. We're solving in a way that recovers Navier-Stokes. In fact, nobody is solving the Navier-Stokes equations. We're all approximating solutions to Navier-Stokes equations. If someone were solving it, they'd have a Nobel Prize. Okay. Some people solve this equation by discretizing the domain and using finite element schemes. Some people approximate solutions to Navier-Stokes by doing finite difference schemes. We use a Boltzmann transport equation, as it were, because of its locality, because of its trivial parallelizability, and solve the Boltzmann transport equation in a way that recovers Navier-Stokes. So are we solving Navier-Stokes equations? We're solving the Boltzmann transport equation in a way that recovers Navier-Stokes equations. Nobody's solving Navier-Stokes equations. We're all approximating it. But the Boltzmann transport equation has advantages because A, it's second order in space and time, and B, it goes hand in glove in a GPU environment. And this has been discussed in decades past. And again, why? Why do we do this? Why do we use Boltzmann transport equation? Because it's so amenable to GPUs, right? Like, Boltzmann doesn't make a lot of sense. It makes sense, but like, it makes a lot of sense when your GPU is available to you. It makes tons of sense on CPUs, but it's a no-brainer on GPUs. Specifically because it's trivially parallelizable and because it's compute dense. It doesn't have these long kind of tridiagonal matrices we're trying to relax. We're just solving, essentially doing matrix multiplication at each lattice point. Okay, and the results mean we get something that looks like an experiment. This is a very simple simulation here, just a free surface, as it were, but watching the time evolution of the free surface, validating the depth of that vortex, as it were, is a routine application of a tool like this. Watching a time-accurate flow simulation, a complex topology here. This is not a standard system. It's pretty well mixed, but it's not standard, as it were. And watching how particles move, we're going to be getting this today, evolve through the system response to agitation, as it were. Like, this is standard. This is lunch fare for M-Star because, again, we're solving these transient equations. Looking at kind of reacting systems, adding some sort of, A to a B to yield a C, and watching how this reaction evolved through space and time, and seeing the competition between reactions, mixing, dispersion, etc., and looking at some of the stratification we see due to poor mixing in this particular multi-impeller system. Like, the important point is we're moving way beyond just like a picture of the flow field. We're moving way beyond like a mean description of strain or some sort of correlation for looking at EDR's function impeller speed. And we're marching straight into, three-dimensional time accurate process simulation. Like that's where this is going. Let's talk about this in the context of RTDs. So we're talking about open systems today. And this is kind of Chemical Engineering 101. Go on to AICHE's Essentials of Chemical Engineering for Operators. One of the first topics is residence time distributions and what we're expecting to see inside vessels. In many cases, when we're looking at open systems and trying to characterize the performance of these particular systems, we characterize that performance using an exit H distribution or residence time distribution, sometimes used synonymously and colloquially. This describes to us how long, on average, fluid parcels are staying inside the system, right? For a well-stirred system, an ideally stirred system, as it were, we can predict what the exit H distribution should be from first principles. And we know it's going to be some exponential function. This is semi-log here note, wherein the age of the molecules, right? The fraction of those old molecules that leave the system, fewer old molecules leave the system is basically what the plot's telling us. So foundationally, if we have non-idealities, such as bypassing, short-circuiting, or if we have some sort of dead zones, as it were, that can lead to deviations from this ideal well-stirred expectation. And again, we're not going to achieve this ever, but we can if we have well-stirred batch systems. And so the nature of the RTD is commonly used to infer physics of what's going on inside the vessel. And so again, and if anyone, I can send someone's link to this kind of video on YouTube. It's pretty cool, where they kind of do a series of experiments looking at different sorts of like RTDs, and as they inform, as they can use to infer what's going on inside the vessel. This is simple plug flow with dispersion, as it were. But foundationally, the RTD we measure is typically used to characterize what's going on inside the vessel. So for example, if I've got some sort of channeling with dead zones inside this packed bed, I can get a very funny, I should say, exit H distribution that's nothing like a plug flow, for example, but gives some clues as to what might be going on. Tau, of course, is representative of our mean flow field. If I've got, and we're going to talk about agitated vessels today, if I've got dead zones and or channeling, the actual distribution of my exit age, right, is not going to look like an ideal system. I'll get bypassing and some long-tail dead zones you'll show momentarily, reflective of the non-idealities in this particular blending system. And so in a lot of cases, I won't say the state of the art, one of the more common approaches for analyzing what's going on inside the vessel is look at the RTD and then make inferences about how its deviations from ideality are being informed by flow structures inside the vessel. It's okay, this isn't bad. You can do a lot of diagnostics using RTD, of course, but foundationally we can get more. Let me go ahead and kind of clip on through this. So let's take a deeper dive of the agitated vessels in particular, which is what we're going to be looking at today. Dashed line is that exact solution I shared earlier, right? You can derive that from first principles. Black line is what's measured for I wouldn't say atypical, but I'd say poorly performing continuous flow system. When we first inject the dye at time, this is taken from Pip Jones' thesis. I've got 4 snapshots here from his thesis. Snapshot 1 is right as the dye is being added. Snapshot 2 is right when the addition completed. Snapshot 3 is when we have an a heterogeneous distribution. And snapshot 4 is when we're pretty uniformly distributed. Like, this is not an ideal mixer, obviously, right? Not that we'll ever get an ideal mixer, but we see we have some bypassing early into the process. We have non-uniform distribution at some middle time in the process. And then eventually we snap onto the well-stirred limit. Now, luckily, as part of this thesis, they had a clear tank. We often don't have clear tanks. So we have to infer from the shape of this distribution what's going on inside the vessel. Okay, here we see at early times that we are not at the ideal expectation. Well, that makes sense. We haven't yet reached, the inlet hasn't reached the outlet, as it were. There's some sort of time of flight. We're below the expected value because we still have fluid from the inlet trying to reach the outlet. Even at 2 here, we might, depending on where you count 2, maybe 2 should be right up here. But I'd say between 2 and 3, the outlet is becoming aware of the inlet, and eventually it's overshooting. So again, we have this oversaturation of dye on the right-hand side of the vessel that's leading to an overly high concentration of fluid leaving relative to the well mixed state. So we have an overshoot here. Then eventually, as time goes on, we get a well-stirred system here, we snap on to expectations in theory. But it's oftentimes this physics here that is the problem that we got to investigate and understand what's going on. And so foundationally, if we don't have a clear tank, we can use this to back out what might be happening. But this is kind of our diagnostics here. So look at the RTD to figure out, well, I had a time of flight, I had an overshoot. Maybe we've got to change the momentum ratios here in terms of inlet momentum ratio and impeller sheet momentum ratio to get this guy balanced. And that's kind of the topic of this paper down here, which is great. CFD allows us to see inside the tank and understand what might be driving this. So here's a simulation of that same system, kind of watching just the fluid flow, watching how it evolves. And we can see, okay, we can see what obviously the flow pattern that are driving some of these physics in terms of the jetting as well as the bypassing. And we can actually do RTD in simulation as well. Here I'm going to let this thing cook for 15 seconds, then I'll shoot in particles. Now I could do dye or particles, but the advantage of particles is they're all tracked and named. I can track every particle, watch where it comes in the system, when it came in the system, where it went in the system, and more importantly, when it exited the system. I can track the age of every particle upon exiting and reconstruct, therefore, a residence time distribution or a mean exit or an exit age distribution. So I can use, so these guys had a clear tank, which is handy. We can simulate their results and validate against the results and make sure, okay, we can correctly produce their overshoot and their expected mean residence time. But importantly, a lot of our systems aren't clear. And so we can validate against systems that are clear. We can use this approach to understand systems that aren't. And importantly, we can use particles or scalar fields, but we can do this. This is a thing. This is in play. It's easy for us to be able to track particles coming in. It's easy for us to be able to track how old they were when they left, be able to construct what we measured experimentally or inferred experimentally. I showed these slides a couple months ago, but I'll just speak to them again. We use these models all the time to predict RTD. So here I've got data courtesy of SPX, where they have a intentionally designed 2-impeller system with a spinning profile that is tuned to produce essentially 2 separate mixing zones. So the net effect is that their expected mixing profile shown in red, their realized mixing profile shown in blue, mimics one shown in red that is 2 tanks in series. Okay, so this particular configuration allows them to realize a 2 tanks in series RTD, right, with only 1 tank, the appropriate counterflow configuration in the flow field. And so again, it's a pretty complex configuration, but it's something we can handle. I'll jump ahead to this because I showed it during our last seminar. But here again, I can shoot particles into the system while monitoring the time evolution of the flow field. I can watch these particles evolve through the system. I can record these particles as they exit the system, and more importantly, record the ages of each, right? And then I can construct an RTD from that data and see that I can get it pretty good. In fact, the green is what we're getting out of the simulation. And this is kind of cool because it's a pretty complex flow field. Like you've got to get this nuanced 2-zone flow field right in order to recover this kind of neat profile that mimics a 2 tanks in series RTD. But again, I've shown this before. We talked about this a couple months ago, but the important point is this, is RTDs are great. They're easy to calculate. They're bread and butter M-Star, and they do provide insight into what's going on inside the process. You can see I'm kind of building towards something. What I'm building towards is something I think is really cool, that I think it deserves a little bit of shouting, is in that of mean age. This is not a new thing, okay? Mean age as a concept, which is describing the mean age of the fluid exiting the system and the age distribution of the fluid across the system and the side of it, is a pretty old concept. 70 years, I don't know if people want to say 70 years old, 71 years is old. Maybe it's old, but it's been around since the idea has been in play, from volume 2 of chemical engineering science. Okay, it's pretty foundational. And this idea that, okay, even though we have kind of a residence time distribution and an idea of a mean residence time, we know that there are different regions inside this vessel, even a simple pipe with laminar flow. They're going to be where fluid's going to spend longer, right? We might have regions or dead zones or regions inside this vessel where fluid won't have the same flow profile and therefore molecular age as some other regions of the vessel. And in this kind of earlier paper, there's nice analytical solutions given for standard pipe flow configurations. I would say that mean age was rediscovered. I use that term lovingly by Minye Liu, probably about a decade ago. And when I say rediscovered, I mean it's the same way Elon Musk rediscovered the electric car. Like he didn't invent it, but he made it he presented it in a way that made it understandable to the modern human. And that's what Minye Liu did. And I don't know if he's here. I don't know if he's in the call. He's probably not. But either way. But foundationally, I like Minye a lot. I consider us friends. But I hopefully wouldn't mind me speaking about this. But I think he'll claim that he didn't claim to invent it. But what I think he did is he claimed to make it understandable or at least practical. And he did it by combining, this theory with, at the time, RANS-based simulation to use the fluid field to predict an age distribution. So what this color here, this is velocity, that's self-obvious. What we're seeing here is a mean molecular age of the fluid across the vessel. Blue represents young, new fluid. Red represents old fluid. And what he's seeing here is that he gets stagnation regions where the fluid tends to get stuck. Not stuck in a mass conservation problem way, rather stuck in a way that we have molecules here tend to be old. They've been in the vessel for a long time relative to the molecules coming in, obviously, right at the inlet. And so what you could do with this is understand the effects of bypassing and whatnot on the age distribution and residence times. And so foundationally, if you just put dye in here or did some tracers or whatnot, yes, you get a mean age distribution, an exit age distribution. Yes, you get a mean residence time, which certainly should bounce with what mass continuity demands. When you start to kind of pin on some of the mean age, now that it's so illuminating, you can not just see, not just the what, but the why and the where. For example, why is the mean age this value? Where is fluid getting stuck? And what implications might that have on, for example, a chemically reactive system? If molecules here have been in the system 10 times longer than molecules here, well, that's going to form reactions inside this zone. Likewise, the molecules here are getting trapped, proverbially speaking, relative to the molecules racing around that bulb, as it were. That's going to form reaction kinetics in this zone as well. So what's neat about this type of work is you can actually see, what flow physics are driving variations in RTD at the exit here. And so we wanted to see, and Minye and I gave a presentation a couple of years ago on this, is could we generalize this to transit simulations and really link this age profile and age distribution to what was going on with the measured exit ages. So to do this, let me just explain briefly what mean age is and this idea of this local age. Okay, pretend I just have particles going into a vessel here. These are just massless tracers, so think of them as nothing more than colored fuel fluid molecules, as it were. As time goes on, the color of the molecules is getting warmer, okay? So newer molecules are red, older molecules are blue, okay? And I got dark red there. As I play this guy, you can see that in some regions of this vessel, particularly right behind this tab mixer, I'm lagging. I've got dark blue, despite the fact gray is coming in. I've got dark blue particles just hanging out here. If I continue to go on here, I've got dark blue even as I got pink throughout the rest of the vessel. I can see just through in this picture here, if I drew a series of control volumes, the average age of the molecules inside that box would differ across the system. So again, if I drew a box around here, the average age of those molecules is different, is younger than the average age of the molecules inside a box down there. So even though the mean age of this entire vessel is going to be well defined and informed by the flow rate ratio, there are going to be regions where the average age of the molecules is higher. All right. And so if I derive a little box here, I can calculate what the mean age inside that box will be. That mean age, well, is nothing more than the total age divided by the mean number of particles, as it were, right? And that can vary over time. But for each individual box here, I can define what the average age of the molecules or the particles of that box will be. I can do some normalizations here, right? I can convert these into something like a concentration by dividing by volume. That's fine. I can divide the numerator and denominator by volume. And so the denominator is pretty familiar. That's just a number density or concentration. The numerator here, this is something that Mignet called the molecular age, as it were. So think of it as this kind of volume averaged age, as it were, termed molecular age. These define a local property. So again, at each position, I can do this reduction, right? For any number of voxels, as it were, I can do this reduction and compute my molecular age divided by my concentration to compute my mean age, as it were. I can do this across continuous scalar fields, right? Assuming I'm solving the transient fluid flow solution, I can solve for the advection of species concentration coming in. I can also solve for the time evolution of the age, right, coming in. And I can take this molecular age. And I can take the ratio, of course, to get my mean age. And if you squint at this, you can see kind of what's going on. Like if I have, this is advection diffusion, that's immediately recognizable. This one here, like, what's that plus C doing? Well, pretend we have a static fluid field with no kind of advection or whatnot. You can see, I see. Like this is essentially a source term to age, right? The time rate of change of age for a static system is going to be related to the current concentration inside that system. We can see how these cobble together. We have concentration, and that concentration integrated over time leads to my molecular age. And that ratio of that mean age of that molecular age to that concentration gives rise to my mean age, as it were. I'm moving through this kind of quickly. It's in the literature, in Mignet's literature. I can point you to that literature. But foundationally, if you think about it this way first, just as some voxel with some average age of the molecules divided by the number of molecules in it, that's kind of the first kind of hook you can get into. And all this generalization to continuum fluid flow, it works as long as you keep anchoring yourself back to the idea that it's just the average age of the molecules inside that voxel. So what does this look like in action? What it looks like is this. Is here I'm calculating mean age over time, and it's going to take a while for this figure to come into play because it's got to kind of mature into a steady state. Here you can see it. So here I'm watching mean age evolve. Here near the inlet, the average age of the molecules, right here in this inlet, like always close to zero. Like we always have fresh molecules coming in over time. Here near the exit, we've got, I should say near the back, we've got older molecules. These molecules are kind of hanging out. These have been in there for like 40 seconds. Like the stuff back here, it's been in here for 40 seconds. The stuff right here has been in there for a fraction of a second, as it were. The stuff on this side has been in there for about 20 seconds. And look at this. This is so interesting. I got to look away from the camera. But what you see at the exit here is what you're getting is kind of a cross-sectional mix of young, middle-aged, and old molecules leaving. I think it's cool to see that. Like you can see, okay, there's some that are getting siphoned off this bottom kind of dead zone there, as we're leaving at the bottom. We got a mixture of some snaking through the top, but it's neat to see we're not getting the mean molecules at the exit. We're getting a mixture of old, young, and middle-aged, which are convoluting in a way that recovers the mean, which is kind of cool, I should say. And to see that distribution across that outlet and across the vessel, I think is really cool. And you can do analysis with this. Like, for example, I can take the mean, the mixing cup mean of that fluid coming out, and I can compare it to the distribution of ages across the vessel, and lo and behold, and this makes sense for the conservation of fluid, that the mean age of all ages given the distribution matches the mean age of the fluid exiting, which matches the mean residence time, as it must for the conservation of mass and volume. But it's kind of cool to see, okay, when I have this mean coming out the outlet, it's not like all green, right? It's not just like, it's not like this nice, I should say, it's not all like this even yellow. It's a mixture of green, yellow, and red as it were coming out. And being able to see kind of the distribution driving that mean and where the dead zones might be is really cool. And it's potentially, as a complement to RTD, very illuminating. And what's neat about this approach is how it scales so well with complexity. Okay, so in this system here, I've got a non-Newtonian fluid, whatever. I'm going to have these impellers like turn off after 30 seconds. I'm going to inject dye, or rather some fluid at the top here over like a burst for 5 seconds. And then I'm going to drain things in 20 seconds. Drain things off at a common speed here. And mean age, like the RTD, okay, like this is a pretty weird RTD to do. Like, yeah, you can do it. You can do it. You can shoot particles in and calculate RTD. But like, I don't know exactly what you're comparing to. All right. Yeah, you can maybe compare it to a well-served mixer with a mist system with some sort of time evolving concentration. But like, it's not immediately obvious what the RTD should look like, especially during initial boot up conditions. Well, with mean age just comes to life. So let me show the velocity field to begin because it's so interesting. Here I've got my impeller spinning. I've got a free surface that's going to start to wiggle here once the vortex, there's no baffles here. And so the fact that the impellers are off-centered and angled mean that I get subvortexing, but not a big center vortex. There I'm adding my fluid there. And then at 20 seconds, I'm going to start pumping the stuff out. Okay, I'm pumping it out. So now the fluid level is going down. My impeller is going to cut off at 30 seconds, as it were. We'll just cut it off here, and then I'm just going to be draining the fluid for the duration of the simulation. Okay, impeller's off. Vortexing stopped a bit. But again, here's kind of going back to the GPU thing. Like, I want to emphasize this point. We got a lot of people in this room that understand this point. Some that might be new. I know we have a lot of new faces. But, like, we're modeling a process. Like, we're actually instructing over these minutes of operation. This is what the vessel's doing. That's kind of cool to see. But here's mean age. It's amazing. It's interesting to me. And so there's the velocity, all well and good. Fluid's getting pushed around. Here we've got, dye coming in. It's going to shoot here in a minute. I guess at 10 seconds it starts. Here's a little nozzle doing its happy thing, squirting fluid in. It's going to shut off, and then eventually I'm going to drain this vessel here at 20 seconds. I'll begin to turn on the pump, and I'll pump out the fluid, assuming that's been well mixed, and down it goes. All well and good. Mean age is interesting. So again, let's watch this. So there's no age anywhere yet because I haven't added it. I'm looking at the mean age of the fluid coming in this inlet here. Let's have it come on down. It's going to shoot in. Okay, there it goes. So, okay, look at this now. So I'm looking at one plane. So we're getting what's come to the cut plane here. Okay, let me pause this. Okay, here we can see already, like this stuff is aging uniformly, right? It's the injection stopped. So everything's aging uniformly. But to be sure, we do have stratification inside the system because not all fluid came in at the same time. So as I go through time here, like everybody is aging. The whole system's getting to warmer and warmer and warmer colors, right? As it goes through time, I'm crawling up this mean age because the fluid's getting older, right? And eventually I can see they've kind of washed out the age distributions. But at intermediate times here, I had this really cool convolution of age distribution superimposed with just continuous age growth as the clock turns, right? As the clock turn, as the hands of the clock turn, this thing's getting older. And then to see eventually as time goes on, this guy start to kind of homogenize in age, such that the product we're exiting is indeed indicative of the mean age inside the vessel is really compelling. Maybe I'm just super excited about it. Maybe I had too much sugar in my cereal this morning. But I think it's really cool to be able to see, like, all these physics at play, the constant aging of the fluid once it's well mixed and throughout the whole process, the heterogeneity that exists during these initial timescales. And what's neat about this is like this makes sense because we're not trying to pin some theoretical RTD into this. We're actually looking at the age distribution across the vessel. Let's do a working example of this. Okay, so here is I'll just show you kind of how this looks like as it evolves to the system. Here is a very simple baffled pipe. I've got an inlet in there with just some velocity boundary condition of 1 meter per second. I've got an outlet just at pressure. I've turned on mean age and M-Star. So I'm going to here turn on mean age. And I have to tell the code, like, where's the mean age source and what's not the mean age source. The outlet is not the mean age source. The inlet is the mean age source. I'll use Van Leer because I'm actually solving this as a continuum. This system is 3.1 meters long. My initial velocity is 1 meter per second. I already know my mean age at the exit has to be like 3.1 seconds, period. That's inarguable. I'm doing age. I'm also kind of dumping particles in here just to show you like what the particles are doing as well as we attempt to calculate an RTD. So let me run, and I did like feed and dump. I don't need them both. I was just feeling excited. I'll just do dump. Let me just disable this. I'll just do dump for the time being. I'll just dump one part. I'll just dump in 100,000 particles at 1 second, and I'll start my mean age calculation in 1 second, which should be enough time for this guy to reach some sort of steady state. So let's run this guy here. I'm just running this on my laptop, so I'm not going to set any land speed records here, but it'll still move. It's a decent sized laptop. Okay, off we go. So at the end of the day here, we're marching through time. I'm moving at about 1.2 billion updates per second, which isn't bad. I don't have any moving bodies here. That helps me run a little bit faster. But to be sure, I'm moving along. I'm about a quarter second in. Let's go to post and watch this process evolve. So here I go here. Okay, so I've got my fluid beginning to evolve. I gave a little bit of ramp to the inlet, so we'll let that guy cook and reach some sort of steady state. I'll reload here. I'm coming up on half second in. So my velocity is starting to mature as I move through this guy, right? I'll do like a two-plane action. So I'm going to do age on that guy down there below. So I'm moving through about 0.7 seconds in. Let's go ahead and kind of play this guy. And importantly, guys, I'm iterating through time here. Like this isn't a pre-canned solution. I'm actually solving this like right now, which is incredibly dangerous to do. Kind of put your heart in the hands of Microsoft and whatnot. But either way, I'll let this go. So I'm at 1 second now. So at this point in time, I've shot in my particles. There they are. I can see my particles, and I'm going to colorize these just by like maybe I'll just it doesn't really matter what they are, but they're just random colors right now. I shot them in, and they're starting to move downstream. Let me turn off the velocity field because it's not super important here right now. There are my particles kind of coming in at 1 second, and they're racing downstream. And so they're kind of shooting down, getting trapped inside these bins. And I'm going to be able to calculate the age of all these particles by looking at, rather I should say, the exit age by looking at the time which they exit minus the time which they were entered. And again, so the process is evolving now. They're still kind of moving through each like baffle, boom, 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 moving on down through. We've got some lucky winners here that just shot right through. Like a couple lucky particles are just moving right through that kind of fast moving core. Let's take a look at the mean age now. So I'm going to turn off the particles and look at just the age on this guy here. So instead of velocity, I'll color by mean age. And let me choose like a little, I know this guy's got to get up to like, I'll use 3.5 as my high watermark because I know that's where I'm going to go. But I'm kind of like getting there. Okay, so here I've got particles kind of rushing through. And here, and let me bring this down just so I can speak to it real fast. Okay, here I can see the age of the molecules as they come in as well. So look at that. I'll pause this moving fast. Sorry, you got to really have a trigger finger. Okay, the molecules down here are like 0.7 seconds old, which makes sense because I started the injection at 1 second, as it were. The molecules here are only like 0.4 seconds old. The molecules here are always fresh and new. So if I go through, I can see like these molecules getting older and older and older as they go through the system. And eventually they exit, right? They exit with a certain, they made it on out. They made it on out. I'll let this go here. And I'll kind of calibrate this back to what I know my truth to be. I know I've got to have like a 3.1 second mean age upon exit. Here I see the particles as well. So I'm watching the particles come on in. They're shooting through, going through each of these bins. And I see this kind of like additional delta function kind of spreading out, as it were, as it interacts with each of these bins. Now I'm starting to get some particles exiting, right? If I go to my particle count, I can see I shot them in at 1 millimeter. I'm sorry, 1 centimeter. I'm sorry, 1 second. And then it took, let's see what I got here. It took like 0.9 seconds, 0.95 seconds for the first one to cross the finish line. Okay. So like my minimum time of flight there was like about a second, as it were. And some of those lucky winners just shot through the center of those baffles and rode along that fast moving center. Now I have particles exiting. This exit profile, this change in particle count, this data here is how I construct my RTD. Let's take a look at exit age here as this kind of comes into play. This guy's still booting up. He's still kind of figuring out what the exit age distribution is, rather what the mean age looks like as it evolves in time. You can see how it's shaping out. I've got some regions here in these earlier bins where fluid molecules tend to hang around. Like look up there, I've got like these molecules here, they're like 1.5 seconds old. And you can see that in the particles here as well. We're getting particles trapped there. Like I can see, okay, like particles are getting, like if you have just the particles, oh, they're getting stuck there. Well, with mean age, you can see exactly how long they're staying. Like the molecules there have been sticking around, well, they've been hanging in there. Their average age is 1.5 seconds, as it were. As this guy continues to churn and convert towards a steady state, I'm watching each of these bins eventually mature towards a well-defined distribution. Now, of course, all these particles are eventually void in here. We're getting that kind of the main lump out. We'll let those go on through. And eventually these particles will all exit. And the mean residence time of all particles will certainly be 3.1 seconds. We can see right now we're getting some sort of a profile here, which I'll analyze momentarily. Let's take a look at this age. Okay, so here is the age, the average age of the fluid leaving the system. It hasn't yet converged. It's not yet settled into where it needs to go. We already know where it's going to get. We know this number. It must converge to what? Right around 3.1. It must. The average age of the molecules leaving the system must be 3.1. Why? Because the length of the system was 3.1 meters, and the superficial velocity was meter per second. We know the answer already, but knowing the answer isn't what we want. Because more importantly, we can see the variations in the age across the vessel as this guy boots up. So it's not surprising to me that we're only 2.8 seconds into our mean age calculation. And so we haven't yet been able to achieve that. We're going to have to wait at least probably 4.1 seconds until we start to approach and dogleg towards that mean age converged value. So in the meantime, while letting that converge, let me show you how I'd convert this into an RTD. And so within M-Star, obviously, oopsie, I don't need to post that again. Let me open this up. Open up in this Excel here. Let me go to my stats. We record, all of these exit statistics, right? Should you have this turned on, of course. But I can go here. Let me go ahead and kind of put this on. So here I have a list of every particle that exited the system. I have its ID, where it exited, when it was added, its diameter, volume, positions, velocity, etc. So realistically, the first particle to cross the tape, crossed at 1.92389 seconds, having been added at that time step, which for our purposes is 1 second. So the minimum time of flight was 0.92 seconds. All of these guys kind of came in later and later. We've got some stragglers. This guy, particle number 86931, which was the 56,000th particle to exit, he was hanging around for 3.2 seconds. And as time continues to go on, I've got more and more of these stragglers coming out. So I've got about half of them voiding now. So I'll go ahead and kind of grab this data and just replot it here. Where am I down to now? Let's see what we got. I've lost about, sorry, what line am I on? I can't see that with my, I can't see what Selman, the red line's changing it. About 82,000. I've lost about 82% of my particles. And I can see some of these long tail ones. Let me jump on down here and kind of continue off this difference calculation to my age. Okay. So I'm not totally done yet, but I can begin to see this number is going to be a little bit low, below 3.1, because I'm waiting for these last particles to exit. I'll just tee this up as I'm getting ready for the 3.1. So right now it's 2.6 because I've got to get the rest of that tail. But you can see why this average exit age is driving towards 3.1 because conservation of mass demands it. In fact, I can do a histogram here and begin to see what my RTD would look like. An RTD, as the name suggests, is a residence time distribution. So I will calculate a series of bins. I will go to my data analysis here, and I will calculate a histogram. Let's see, I'll use N. I will use S here as my bins, and I will be able to construct then my histogram. So here is, as calculated from the particles, the RTD of this system. Okay, I can normalize this, of course, but this is the time. It's got this thing right there that's messed everything up. This is time in the x-axis. This is the number of exits, as it were. This is my RTD. And you can begin to see now there's going to be a longer tail here, of course. This is not going to be symmetric. There's going to be a longer tail here. But you can see the effects of that kind of baffling on perturbing this from delta to long tail schmear, as it were. Let's just see how far we've come along. We've got only 3,000 particles left. We've got most of these guys voided. Let's go ahead and kind of do one last RTD for good measure and see where this falls in. Let's go up here, put this down here, and buzz on through to exit these guys. And we can see here, now we're getting some of our longer tail. right? We're getting some of our longer tail particles exiting. If I look down here, I've got some, some have been hanging around for 5 seconds at this point. So let me just recalculate this histogram and see how it informs us. Take a look at this one more time. We can see the formation of this tail. Okay, we can see it coming down. So kind of interesting to see, right? We can actually calculate the RTD directly from the particle ages. And I'll maintain, this is cool. It's neat to do this, and it's very familiar. But I really gotta mention this mean age again, watching it converge here. So here I've got, I see my outlet. Okay, I'm starting to snap. Oh, there it is. Look at this. I can see my mean age kind of crawling up, crawling up, crawling up, and I know this. Just as like this mean value, if I go up here, this mean value as I get all those particles out is going to converge like 3.1, right? Per the conservation of fluid. This mean age is going to snap into about 3.1, as it were. But the mean is, we knew the mean just a conservation of mass. What's really interesting here is that we can actually see now the distribution. And so this is almost there, but I'll go ahead and play it one more time. So I start the mean age at 1. I've got all these molecules coming in. I can gradually see it aging, as it were. And eventually it's right about now, it's reaching like a steady state, a steady age distribution. And I can see in this first bin here, I've always got kind of young, fresh fluid. In the second bin down here, I don't always have young, fresh fluid. These in the core region, I've got young, fresh fluid. But that young, fresh fluid punctures all the way down to the third zone here. Look at that. In fact, let me colorize this in a bit more kind of explicit way. Let me use fewer bins. Like, I've got young fluid pushing into bin 4, right? And I've got what would be bin 5 fluid hanging around in bin 1. Like, and that's hard sometimes to infer from just the RTD. The particles gave us a clue, right? If I watch these particles here, let me make them a bit bigger so you can see them more clearly. The particles gave us a clue as to what was going on. They gave us a clue that something was hanging out there. They gave us a clue that was sticky, as it were. And eventually they do void, which makes sense. Eventually they get swooshed out. But foundation, to be able to then quantify, like, oh, we have a mixture of zone 5 fluid in zone 1, and we have some zone 1 fluid in zone 5. You know, quantify and assess that, that's pretty compelling, I think. And be able to see the full physics driving that, I think very interesting. So at this point, our RTD should be all but complete. We've only got a few particles remaining inside the system. We've voided all but 218 out of the 100,000 we put in there. And at this point, our mean age is snapping into place as well. Yeah, we can see it going right to that 3.1, which is exactly what we suggested, as it were. So if I pull these particles in to do a final RTD, let's pull them on in here. Plop this on in. One thing I don't like about Excel is I have to, like, I don't know, maybe, I guess if someone knows more than me, which I'm sure someone does, they probably can do that more cleverly than I can, but I always have to redo it. Okay. I think more particles might have allowed me to do a better job of getting my exact mean, but I'll take 3 against 3.1. I'll take 3 given the discrete sampling. There are some long tails here that are really taking this thing a while to go. Let's go back to data analysis, and complete our histogram here. We can begin to see kind of how this is coming together. I should have made this a bit longer, because now I'm actually at this long tail where I've got particles that are 6, 7, 8, 9, 10 seconds old. So let's try that one more time. Pull this on. I'll just let it go forever. And I'll bring this down as well. So now we can see, as this dust settles, like the RTD. Like, that's the RTD coming from particles, right? And I'm sure people understand this. Let me just, this is time. That's number of particles, as it were. But more importantly, being able to see this age distribution, I think, is pretty compelling. And snapping over to a 3D volume now that it's fully converged. Let's take a look at it here. There's our velocity. I think it's really neat to see that velocity shoot those baffles. Then going over to mean age and watching. Let me colorize this again one more time. Watching how this age progresses. Seeing how I get older fluid kind of trapped behind these baffles, as it were. Super compelling. Super compelling to use those as a handshake to validate RTD, to see what's driving the RTD, to be able to calculate these in one simulation. Pretty neat. Let me go back to the slides and kind of, I'm not going to have time to speak to the mixing, but just as kind of a side note, should people want to explore this further, one of Minier's really neat innovations was that the variance in the mean age gives us a clue into the mixing time. So we can save that for the literature or a sidebar. But if we take the age distribution and look at the variance of the age distribution, we can predict the mixing time inside this open flow system. And that's a really abstract but powerful concept. That is how long it takes for fluid to blend when it's being added into and topped off, or whether it's being added to and drawn down from. Well, that's another discussion that's getting a bit advanced. I'm not going to have time to get to that today. But there are a lot more things you can get from what are called the moments of this age distribution. We'll speak to that later. I'm not going to have time right now. Okay, let's just wrap it up. Open systems are easy to simulate when you can do these time-accurate three-dimensional runs. Okay, the boundary conditions can be time-varying. The flow physics can be time-varying. That's not a problem at all. Importantly, we can do RTD calculations in the exact same way you do them inside the lab. Okay, we can add tracer. We can watch it evolve through the system. We can solve it in tandem with the fluid flow and record both concentrations and or particle ages as they exit. Okay, pretty neat, as it were. We do this apples to apples comparison. There's not something special we do in the simulation. We can just do RTD in the exact same way, which folks would do it inside the lab. Mean age is really cool. Okay, mean age is awesome. I think like being able to see like the actual age distribution of the particles and being able to understand how that age distribution is informing what's coming out of the outlet is fascinating. And I really say, for me, I'm going back in time, like this blows my hair back. Like it brings it to life. Being able to see like, oh, like that's what's the exit. It's not all yellow. It's all colors, right? It just averages to yellow as well. Like that is just illuminating to me to kind of see what's going on to the vessel and how we can fix it. Sorry, I didn't mean to step back on the slide, but I just think it's such a cool point. Explore mean age. I guess it works. It's not unique to M-Star. You can do it in any solver you want to use, but like it works really well in M-Star because M-Star is transient 3-dimensional. It's already built in. So I explored those that have M-Star to use it for your open systems because it's so compelling. Okay, we're at time. I'm not sure if we have time for one question or two. Thanks for joining us. I know this was different because we did the old live demo, which it worked, which was successful, which is good. I'm glad it didn't fail. But I appreciate you kind of having a different workflow today. We're allowing me kind of jump in and actually show how to do this stuff. Thank you for coming. I hope this was interesting. Hopefully you understood how we can analyze these systems, what the RTD is telling us, what the mean age is telling us, how they complement each other. And yeah, any questions you got, we got about 1 minute. Fire away and I'll answer them as they come in. But yeah, thank you so much for tuning in.
Yeah, just one question here, and I want to reiterate too. Great presentation. They said I agree. Excellent presentation, John. I'm sure no one here realized that residence time distributions and mean age could be such a riveting topic, but it's just been fabulous. It's so exciting. So
I don't know why. I don't know.
But so the question is, can we get files with models used in the lecture to reproduce them by ourselves?
Sure. Yeah. Can I put this in a group? Can I put this in the chat? I'm just wondering, like, is that a thing? Let's see if we can. Let's test this. Let's just see what happens. I want to see what it take. I'm just dragging into the message. No, I can't put it in the chat. Just email me and I will send it out to anybody. Okay. But yeah, you can see I'm trying to like drag it in the chat, but it won't let me. Teams is like, oh, let me see if I can attach a file. Can I do that? No, I can't just send a file to the entire group. That's probably good. But either way, I'm sure someone did it and like sued Microsoft. But yeah, files are all yours. Everything I've got here is all yours. And email. Oh yeah, email me, Thomas at M-StarCFD.com. Yeah, shoot me an email.
Perfect.
Okay. Yeah. Thank you guys. We're at time. Email me questions. Thanks for your interest. Slides are available as well. Yeah. Thank you, Amber, so much.
Yeah, thanks, guys. And just for your information, this fabulous webinar has been recorded, so you can watch it again and enjoy it on all those platforms I mentioned earlier. So thanks so much and have a great day, everyone.
Thanks, guys. Appreciate you. Bye-bye.